Hey, I hope you all got to see the eclipse to your satisfaction. I haven't seen it yet. This is Sunday afternoon that I'm recording this, and I won't be here Tuesday, so you're hearing this now because hopefully right now as you're listening to this, I'm with my brother Gary, and we are actually looking for these things. He acquired several feather mattresses from an estate sale, and the theory is you see these coils of feathers in a feather mattress. They're called death crowns. And the paranormal thing about it, which we're sort of trying to debunk here, but the idea is that when a dead person or when a person dies on a mattress or a feather pillow, when their spirit leaves the body, it spirals out some way and winds up these little things called death crowns. And so we're actually going to look at some of these. We have no idea whether someone died in it or not, but we hope we'll find some of these in the mattresses and can do a little scientific research on why these may occur. Anyway, that's totally off the subject of what we're talking about, which is okay because if you recall, we were talking in yesterday's assignment or Monday's assignment about our place in space, obviously. And what I wanted to get across was, while we're still riding this wave of excitement about the eclipse and everything, people are sort of a little more in tune to what's going on in space. And we need that a lot. We need more than just biology and chemistry. So I hope you noticed when we went through this the last time, the incredible sizes of things we're looking at here. So here's the distance from our Earth to the sun. And look at this, the size of our solar system, 7 billion miles, if you consider the orbits of perhaps Pluto and Neptune. And then you zoom out from that, and if you took 900 of those distances, you get what's called 1 light year. So keep that in mind. When we talk about light years of things, we're talking about incredibly big distances. So when we look at stars, like I said last time, this is a picture not of just stars, but this is looking completely out of our galaxy of stars. And every point you see is another galaxy of billions of galaxies. So God is just incredible in his omnipotence and his omniscience, because if you look in Genesis, it merely says, and he made the stars. So it kind of downplays it, but Psalms does say that the heavens will declare the glory of God in some way. Take a look at this video, though. This is kind of interesting because it shows a perspective of the size of the universe in a way that's kind of interesting. Check this out. So we're zooming out from this girl. The line at the bottom shows the size, the distance scale that we're looking at. So at 1,000 kilometers coming up, zooming way out, obviously looking at the west coast there. And now we're going to go even further. So let's keep going. Zooming out from the Earth. And now we see some asteroids coming in, and we can see the size of the solar system. And now we're zooming out of the solar system. 100 billion kilometers now. And again, our sun is just one of many stars. And these are just our neighboring stars, so we're not even out of the galaxy yet. 1,000 light years looking at right now. Okay, now we're starting to see that 100,000 light year galaxy. And now let's even spin away from the galaxy. Look at that, 1 million light years across we're looking at. And let's zoom even further, the cosmic web, 1 billion light years across. This is what we think the universe is actually, probably anyway, looks like, or at least some people have decided that. Okay, let's zoom back in now. Back to Earth. Falling back to the ground. And now let's go negative. Let's zoom into some molecule-sized things. Isn't it interesting? Our bodies are sort of in the very center of the scales of magnitude. So here we are going into the capillary system, looking at a white blood cell, a chromosome, DNA molecules made up of millions of atoms. Down to electron sizes right now. Picometers, very, very small. And now look at this, going into the nucleus of an atom, a femtometer. And then back again. Amazing. Okay, so let's look at some more things now. I just showed you in the PowerPoint, I think, some of the major ideas about what people think about the size of the universe and things like that. We talked about the moon and how interesting it is compared to other moons that we've had. And I hope you understood the idea when we talked about what an eclipse was, what had just happened. So what would it be like if the Earth were in the middle between the moon and the sun? Have you considered that? We have those much more frequently than we do solar eclipses. That would be a lunar eclipse, and that's when the Earth casts a shadow on the moon, and we see the moon kind of eaten away in a way. So let me show you something else you can do. If you have a laptop sometime, I highly suggest that you look at some of these. Look at this first. When you think of a scrambler ride at an amusement park, the one I'm thinking of is the thing that has 4 seats right here, and it has 3 sets of 4 seats on a pivoting system right here. So you probably have ridden this before. You have 12 compartments, 4 per arm, 3 arms. And so what you've got going is this thing spinning and these 3 are spinning, but the whole thing is spinning at the same time. So if you've ever done this, have you ever looked at it and wondered perhaps what that would look like from the perspective, or you know what it looks like. Here's what it is from you, the rider's perspective. So especially look at the background, not the person in the seat, but look at what you yourself are observing as you've got 2 motions, the motion of the arm circling and all 3 arms circling. So one big circle and 3 smaller circles. Now, what if you didn't know the situation and didn't know that you were sitting in one of these 4 things on 3 arms, and you were trying to look at the people rushing by you in the outside world? Do you see how difficult that would be to actually look at this and figure out what's going on? So how is that different then than what's happening with the Earth and the solar system? A lot of people don't understand this concept either. So let's simplify it. Let's just make one circle and we're looking off the circle. So pretend like we're on a rotating object, like the merry-go-round here. So watch this. Now, particularly look at the outside world that the merry-go-round people are seeing. Yeah, so you can see the things happening on the merry-go-round. That's what you see looking around you right now. You can see other people moving around and things on Earth moving. But look off of the merry-go-round at the circle of things going around you that would be hard to see. So could you imagine someone like Copernicus or Leonardo da Vinci centuries ago trying to do something like figure out what's happening in the background right here and try to figure out what your motion is? You would probably get the impression that the universe was going around you and that it wasn't you moving, but it was the universe going around you. And that's the notion that's held for a long time. People have thought that what we see happening above was the motion, when really it was us having the motion. So keep that in the back of your mind as we talk about all of this. That's one of the difficulties of studying astral type things happening or celestial events, because we always think it's happening out there, but sometimes the motion is more of what the Earth is doing and what our motion happens to be at a particular time. Okay, so let me suggest something to you. Go to a site called stellarium.org, not .com, but .org. Okay, stellarium.org sometimes. And if you have a chance, load this. It's a safe program. I've used it many times. It's been invented by a bunch of science nerds, so it's open source, free. You don't have to pay for it. It's very reliable. But I would go to this first one called Stellarium and download the one up here that goes with your computer system. So if you've got a Mac, you're going to do this one. Windows, do this one. Or you can run it on the web without downloading, but I've got this one on my computer. So I'm going to open that up right now and show you some things. So if you download it, it takes a minute to load this thing called Stellarium. And this is very sophisticated. I used to direct a planetarium that had a machine that was probably made in the 80s, and it took an old 286 computer to run it, but it was very awkward, and you can imagine light bulbs trying to project an image of what's happening. This actually does it for you on a computer. So let me show you some things. Right at this very moment, it is about 4 o'clock in the afternoon where I am right now, and this is literally showing me what's happening. I think I still have this set for Rogers. So this is a typical view from Rogers. Now, the landscape isn't necessarily Rogers, but this is showing you the exact motion of the sky, which to me, that's amazing that this program can be so predictive down to the second that certain things could happen. But that's not surprising. We've predicted the eclipse hundreds of years ago, or even thousands, and most people don't know that, but the ancients, such as Copernicus and some others, could literally predict down to the minute when a particular event would happen. That's how accurate the sky motions are. And so people have spent millennia now studying motions of stars and our Earth. Even if they didn't know it was the Earth moving, they could still tell what was happening in a certain place. So in fact, just to illustrate that, I knew when I was 10 years old that this eclipse was coming Tuesday, April the 8th. So I looked it up back then, and ever since then, I've been waiting now, over 5 decades for this eclipse to happen. So there's no way I would have missed it. And that's where I am now. I'm back at my childhood home at the very place I'll go tomorrow to see this, hopefully, in the place that I thought when I was 10 years old that I would be standing someday looking at the eclipse. Anyway, that was my prayer at that time. So look at what we've got here. We've got what appears to be a landscape with the sky. First thing I'm going to do is show you this. If you take the cursor and bring it down to here, it pops up a menu. The first thing I'm going to do is pretend like it's nighttime, because on planet Earth, we have oxygen and an atmosphere that takes light coming in and bends it around and makes it have the blue color scattered. If we were on the moon right now, you'd be looking up and you would see a brightly lit moonscape, but a totally dark black sky. And unless you have an atmosphere, you would see total blackness. So let me turn off the atmosphere. And all you do is come down and click on this one little thing here, atmosphere icon, and boom, we're just like we're on the moon. So this is what it would be like if we didn't have air circling the Earth. We literally could see stars in the daytime. In fact, if you saw the eclipse yesterday, that's hopefully what you saw, was total darkness in the middle of the day here at about 4 o'clock. All right, watch what else you can do. I can take this and push down and left click on it, right click I mean, and drag this around to different positions so that I can see more of the sky, more of the landscape. I can also grab it and pull it from side to side. And if you'll notice, this does have cardinal points here. East is right here, so I'm looking directly east. And remember, like I said, this is very accurate. So if you were to go out right now and look to the east, or actually, if you were to go out on, here we are down here, April the 7th at 1600, which is 4 o'clock, 4:17. Yeah, so that's where we are. And if right now I'm looking outside and it's sunny, so I don't obviously see this, but if I went and looked east right now and didn't have trees in front of me, I actually could see the star Alphard and Regulus right here. And I could look up higher and see Procyon, Sirius. There's the brightest star in the sky except for our sun right there. So this is pretty useful. And we could actually go back and set the date. I'll show you in a minute. We'll set the date for another particular day. Also, let me look directly overhead. So see this? I can pull up and look way up to the center of the sky above me. That's what I'm seeing right now. So I'm going to go back down. Look at this horizon again. Also, if you want to use this someday, you can completely turn off the horizon. So what if we could see through a transparent Earth? We just turn it off right here. And all of these stars you see are what we can't see now because they're below the horizon. I think I'll turn it back on just so we can see. All right, let me show you some other features. And the rest of this time, I just want to show you some things you can do and show you some motions that would be very difficult to see if I just tried to explain it to you. So the first thing I want to show you is this. I'm going to go down and turn on real time. Oh, in fact, it's on right now. Look at this. This picture is actually moving the way that the stars and sky would be moving. Oh, but remember, it's not the sky moving, it's Earth moving. And since we're sitting on the Earth right now, in fact, in Rogers right now, you're moving 834 miles per hour. And if you're sitting in the classroom right now, you're moving toward the front of the room at 834 miles per hour. Obviously, you don't feel that, but if you went outside at night and looked, you would start to see the stars move. Now, I'm going to speed the stars up a little bit. So I'm going to hit forward. No, let me hit fast forward. See a difference? Yeah, look right here. Look how fast the seconds are passing. Still, you don't see much motion, though. If you watch for a long time up here, you could see it. Let me speed it up even more. So let me double that time. Now look at what the seconds are doing. Look what the minutes are doing, 29, 30, 31 minutes. So now do you sort of see a little bit of motion in the stars up there? Yeah, we're going about 50 times faster than typical time. Let's move it one more notch up and watch what happens. There we go. Look at time down here. Look at how minutes and hours are going by quickly. And this is literally what I would be seeing. Okay, so this is actually, and look, it's showing us darkness because this is at 10 o'clock at night right now that we're looking. So we have the southern horizon. I'm facing south right now, and this is literally what I would be seeing on around 6 o'clock. Yeah. Oh, we just passed over to the 8th, so I'm on Tuesday morning right now, and it's still dark, obviously. And the program actually is going to show it lightening up in a minute. So when we hit dawn, around 6 o'clock, you notice around 4 o'clock right now. This is 4 o'clock Tuesday morning, real early. Here we're coming up on 6 o'clock. And watch, the sky is going to get lighter because we have it set to show the actual horizon. So here we are at sunrise, but we still have the stars going over. And if we turn the atmosphere off, we wouldn't see the stars at all, right? Because the sky would be blue, but they're still going around. That's what I want you to see. So I turn the sky off again. The stars are still up there. Oh, and I said it wrong again. It's not the stars moving, it's the Earth. So try to imagine that right now. Those stars are sitting still, but you are on a merry-go-round that's turning at this moment. So just to see if you understand, which direction are you turning right now? Okay, let's watch this some more. I'm going to turn. Yeah, to your left, because it appears the stars are going to the right. So that means you must be moving to the left to see the stars doing this. Very interesting. Okay, let's watch this some more. I'm going to turn. Let's go ahead and turn the. In fact, I'm going to turn something else on. Let me ground back on. So I go back and hit play again, and that takes us back to just regular motion, very slow again. And watch this. Let me pull it down just a little bit so you can see it. In fact, I'm going to turn something else on. Let me stop this just for a minute. So I go back and hit play again, and that takes us back to just regular motion, very slow again. And watch what else I can do. I think I will turn on a grid here. So I'm going to go over to a thing called the azimuthal grid. And look at this. This has some usefulness because tonight, if I wanted you to find Antares right here, Antares is actually the really reddish looking star on the back of the scorpion right here. If you don't think that's a scorpion, turn the picture on over here because we have constellation pictures. Yeah, there's Antares, the supposed scorpion. And constellations, they're an old-fashioned thing, but they're useful because they let us group stars together. And for some reason, the ancients, when they actually saw this group of stars, they kind of imagined they could see a scorpion. So different cultures saw different things, but yeah, you can sort of see the tail of a scorpion right here and the pinchers coming up. If not, that's okay. We just understand today that they're useful in telling us where stars are. All right, so watch this. Tonight, I want you to find Antares. So if I told you, go and look due south, you drag this around a little bit, and you're a little bit off of south. So if you can see the numbers up here, you're about 5 degrees off, and I can't see that very well. I think it's about 160. So if I go this far, I'm about where Antares is. I could also tell someone this is divided into 5-degree squares right here. So if I go up from the horizon about 1, or actually a half, 1, 1.5, 2, 2.5, a little over 2.5 of these units here, and each one is 5, so we've got 5, 10, 15, 20, 5, 10, 15, 20, 25, we're at about 28 degrees above the ground. So if you understand trigonometry and things like that, you can find your bearings. That's the point I'm trying to make. And different people, astronomers who look at stars, they can use this azimuth grid to do that. So let's move around a little bit. And you see the azimuth grid just goes all the way around. What do you think would be the top of the grid that I'm looking at up here where everything comes together? What's that? Yeah, that's called your zenith. That's directly overhead. So if you had the azimuthal grid on and you look at the very center of this imaginary grid that's drawn, you can see that it's in 360 degrees. But the degrees get closer together. It's like latitude on planet Earth. So the same thing you would see on a globe, and they all converge on one point that's directly over your head right now, wherever you're standing on Earth. So let's pull this back down. Try to get back down again. Okay, same motion. And notice the stars are moving. Okay, let's turn the motion on with the grid on and see what happens. So I'm going to go down and speed us up a little bit. Okay, same motion. And notice the stars are moving in different places on the grid. You turn the atmosphere off so we can see it. Yeah, so we got a problem. If I told you to go out and look for which star? Vega right here. You better look quickly because every minute that passes, Vega is in a different position. So bottom line is the azimuthal grid system is pretty good if you're telling someone right at this moment, right on this day, and right at a particular place. But I'll show you a better one in a minute that works even better than this. Oh, here comes the sun. So remember, we're on the moon and we can't really see the color of the sky, but the sun is setting right now. And look where it just set, in the west. And so did the moon. And so are some of the planets we're seeing right here. But so are some of the stars. Now, again, stretch your memory and remember, it's not the sky that's moving, it's us that's moving. So picture your motion right now. What motion must you be doing at this very view you're looking at to see this view? So you kind of see what's happening. You must be rotating upward, sort of. So it's like you're laying on your side, rotating on a big cylinder, and you're seeing different stars appear at the top and disappear at the bottom as they go below you. But always keep that in mind. It's not the sky moving, it's you, with some exceptions. Oh, I see something familiar over here. Look at that. Most of you probably can recognize the Big Dipper. Let's take a look at that. Going over to the Big Dipper. Can't see it too well right now. It's still under the horizon, but let me turn it on again and see if it does something a little bit different than some of the others. So I'm going to speed time up again. Oh, by the way, when I speed it up, this view is called daily motion or diurnal motion. This is the motion you literally would see if you laid out and had nothing better to do than stare at the sky for 12 hours or 24 hours. So if you were just out at night, hour after hour, watching the sky, this is literally what you would be seeing. Okay, let me speed it up, though, so you don't get bored. Okay, so there it goes again. Now, this motion is a little bit different because remember over here, if I'd gone a little bit to the west over here, it looks like the stars are going down like they're setting. But if I go over just a little bit here, how would you describe that star motion? Watch this little star right here. Yeah, it's totally different. It looks like they're kind of coming down sort of, but then they're skinning by the bottom here and heading back up again. In fact, watch this little star right here. It never sets. It just skims down to the bottom, and then it takes off and goes up again. So there's several stars. I would imagine all the stars in this region right through here are never going to set in the sky. If you watch them over and over, you can tell they're always going to be in your sight. And it happens somewhere about right here. There's a line that probably doesn't go below the horizon. Now, the Big Dipper did go below the horizon. Where is it right now? Yeah, you can't see it. So let's wait a minute and see where the Dipper occurs. Oh, I see it already. Here it is right here. Big Dipper. Let me stop that for a moment and take a look at that. So if you've never seen the Big Dipper before, there's one star missing right here, but there it is. The handle of the Dipper, the cup of the Dipper right here. Yeah, let me move that a little bit more. I want you to see something on this. I'm going to take it a little bit below. And you see it kind of skims under this barn too, so it doesn't completely go behind the horizon. Although some of the stars in the Big Dipper do. Now let's get it up inside again. The Big Dipper is one of those constellations that almost every culture has a story about. And I think it's because it's so obvious. When you go outside, it's one of the things that you see that kind of draws your attention. Obviously, it's not a dipper, but it sort of looks like one. So there it is sideways now. And if you want to see the actual constellation this is in, it's actually an asterism that's in the Bear. Oh, you can't even see it, can you? Here's the bear's tail. Apparently the ancients saw a tail of a bear, and here's the rear end of the bear right here. But the Big Dipper is just part of a big constellation called Ursa Major. You'll hear that before, and that's why this is called the Big Bear, and over here is the Little Bear. Now, look at the tail of the Little Bear right here. Got a star right on the end of it. Now, watch this little star and watch the Big Dipper as I turn the motion on again. Notice anything? Big Dipper? Yeah, Polaris doesn't. This star, I'm going to keep my cursor on the star called Polaris. And I'm just going to hover it right there. You're looking at Polaris. The other name for Polaris. Notice anything? Is the North Star. Yeah, Polaris doesn't move at all. So if you're out one night and you're watching a star that just sits and sits and sits and never moves, you're looking at Polaris. The other name for Polaris is the North Star. And look at what we're over. Look at the north right here. So we're looking due north. Anytime you look due north and see a star right here, you are seeing Polaris. And here's Ursa Major again, the Big Bear, the Big Dipper, part of Ursa Major. Let's turn those off for a minute and take a look at this. I'm going to stop it right there. Let me try to stop it 3 days. Actually, I wanted you to see something else here. Let's move it to where we were before. We need to see the Big Dipper for this. Here's the Big Dipper. These are called much too fast, sorry. And if you can't find Polaris, let me try to stop it 3 days from now. Star, it's just a dim little star like some of the others. There we go. But you can find. Okay, check this out. There's Polaris. Here's the Big Dipper. These are called the pointer stars. And if you can't find Polaris, it's not a special star. It's just a dim little star like some of the others. But you can find the Big Dipper fairly easily. So go out sometime if you can see the Dipper and find the 2 pointer stars that are on the cup edge. Doobie is one of them right here. And now watch this. I take this distance and go 1, 2, 3, 4, 5. And I almost hit Polaris. They're not quite lined up with it, but that's a good method of finding Polaris in case you can't find it, because you usually can find the Big Dipper. It's Polaris that gives you trouble, so just find this distance, 1, 2, 3, 4, 5, and you're on Polaris. Now, why is that useful? Well, if you're lost at night, you always know where north is. North is right where Polaris is, because if I turn motion on, once again, notice Polaris is non-moving. Now, everything else does move. It's the only star in the sky that doesn't move. And by the way, remember again, it's not the sky that's moving, it's us. So this is a hard question. Where is Polaris then if it's not moving? Think of yourself on a merry-go-round again. If you're on a merry-go-round looking at your parents on the side spinning around and around, then where was the only place you could look on a merry-go-round that you would see something totally not moving off of the merry-go-round? Yeah, directly overhead. Right? And so what's special about Polaris is there's nothing special about it except that it just happens to be exactly above the North Pole of the Earth. And in space terms, like I said, that means nothing. To us, it's pretty special, though, because when Santa goes out and looks straight up overhead, he will see Polaris exactly over his head if he's standing on the North Pole. So he never sees it to the side or down lower. He always sees it here because it's always going to be over the North Pole, because we are turning on a big merry-go-round and it's not the sky moving. Now, look, the Big Dipper is moving, so Santa would see the Big Dipper go around and around and around Polaris. He would also see all the other stars go around Polaris. So that's pretty important. You can always find north if you know where the North Star is, Polaris. And if you just think, behind you would be south, and directly to your right, east, directly to your left is due west. So you can always find your cardinal positions at night if you can see Polaris. How far above the ground would you look to see Polaris? Can you tell by the scale shown here? Each of these is about 5. So 5, 10, 15, 20, 25, 30, about 35 degrees up. Guess what the latitude of Rogers, Arkansas is? 35 degrees. It just so happens everyone on Earth sees Polaris at the altitude that is equivalent to their latitude on planet Earth. And this obviously only works for the northern hemisphere. So think of Santa again. Santa sees Polaris at 90 degrees. Someone in Missouri would see Polaris at about 40 degrees right here. Someone in Louisiana would see Polaris down here. So not only does it tell you where north is, you can find your latitude by knowing the degrees that Polaris is above the horizon. And your fist at arm's length is about 5 degrees. So if you go up about 10 degrees, so 1, 2, 3.5 fist lengths would be about where Polaris is at any one time. So what do you think the south? Okay, and do you see why Polaris is not over our head? Because we are down from the North Pole to the south by 55 degrees out of the 90. So what do you think the south would look like with this? Let's turn south. I like the south sky a lot because you see a parade of stars just going constantly in the south. Oh, look where the sun is right now. So what time of day are you thinking we're at? Yeah, sunset, because this is west and the sun is on the way down right here. Just so happens other things like Venus are on the way down also. Okay, let's go to south and watch the motion. Yeah, probably so, because the south pole. So there's south. Let's turn on some motion again. Obviously, we're in the northern hemisphere, and we can't see the stars. That would be. Is that what you expected? Southern star, which there isn't one, by the way. Yeah, probably so, because the south pole is down here somewhere. We can't see it because obviously we're in the northern hemisphere and we can't see the stars. That would be the southern star, which there isn't one, by the way. But you can tell it's still going in a big circle, except this axis of the circle is hidden from us in the northern hemisphere. But like I said, the reason I like this, look at what we see. Constellation after constellation just whizzing by right here. And if you're looking south, you don't just see them going in a circle. You see a parade of stars going from left to right. Or if you want to say it properly, from east to west. Because things appear to go from east to west, right? Things rise in the east, set in the west, which must mean Earth is rotating to the west, and that makes it look like things are rising in the east and going to the west. Here's another feature of Stellarium. I could turn on constellation lines if I wanted to. And those are helpful at times. Like I said, they help us group stars together. I could also turn on some names for these constellations. So that's interesting sometimes. You can take your PC outside with you and look at this while you're actually looking at the sky. And there's a feature you can use over here called night vision that allows you to have red instead of blue. And this doesn't mess your eyes up as much. So if you're using your computer outside at night, this is a very useful thing to be using. So you know it's good. You can do amazing things. Turn that off again. In fact, let's stop it. So what else can we do? Stellarium, like I said, it's made by a bunch of geeks, so you know it's good. You can do amazing things with Stellarium. In fact, let's back up, and I'm going to hit the thing here that puts us back to, let me find it again. Let's watch what's going to happen with the eclipse. Oh, here it is. This puts us back to the present day. Okay, so here we are again. Notice back, and today for me is the 7th. So this is Sunday, the 7th. Let's watch what's going to happen with the eclipse. So if you've already seen the eclipse, let's turn off some of these lines here. Let's turn off this grid. Oops, wrong one. And let's just look at the sky itself. And let's set up some other things. I'm going to show you something on here that's useful to you. Let's turn off this grid and turn on a different grid that shows us this. Now, what do you think I've just done here? I changed the grid. This grid is actually based on the plane of the solar system. So remember, the Earth is 23 degrees off of what the rest of the solar system is doing. In fact, say it this way, the Earth is tilted 23 degrees to its orbit around the sun. So the original grid we used is okay. I like this one better though. And I also like to do this. Let me go to Tools over here. Oh, and look at the many things you can do here. You can change the Milky Way brightness if you want to. You can change the view perspectives that you're looking at. You can turn stars on and off. So if I want to turn the stars completely off, I could do that. I can make the stars twinkle like real stars do. I could add labels and markers to stars. So basically anything you want to do here. I could also go and look at solar system objects right here. And so I could look at the major planets. I could simulate light speed. Basically anything I want to do. In fact, let me do something right now. I want to see a scaled moon from now on, and I want to make it fairly big. So let me see if I get this right. I'm going to experiment with it and see if it turns out the way I want. So let's make a big moon. Oh, you could also show markings such as, and I want to turn on a thing called the ecliptic right here. We'll talk more about this later. But there's the ecliptic line. Let's get rid of some of this. And let me do some daily motion. And we're looking south. Let's look toward the... where are we? The east right here. And look at this thing called the ecliptic. So keep your eye on that. Let's also see more sky. There's the ecliptic. And remember now we're on this thing called the ecliptic grid. So I'll start up motion again. Let's see how this is different. Speed us up a little bit. Anything interesting happening? Still see stars. Let's wait for it. We're looking east. There's a star rising, Spica. So anything interesting happening? It appears things rise in the east. Still see stars. Let's wait for it. We're looking east. There's a star rising, Spica. And remember, it appears things rise in the east because the earth is turning toward the west. Antares again. Back to east. What's going on? Oh, look at this though, where the line has moved all the way from east to over here now. Mars and Saturn. Oh, Venus. Oh, and look at this. What day is it right now? Back to east. What's going on? Planets. Look at this. Mars and Saturn. Oh, Venus. Oh, and look at this. What day is it right now? I've gone around once already, so we're already on Tuesday at 10:02. You got it. Remember, I'm on Sunday right now, and right at the moment, look at, oh, I'm sorry, look at this. I've gone around once already, so we're already on Tuesday at 10:02 for Rogers, Arkansas. Look at what the sun and the moon look like, because remember, we still have the moon, and if you recall yesterday's assignment, we are looking at the back of the moon right now. So that shouldn't be hard to understand, because look at this. The moon is very close to us, about 200,000 miles. The sun back here, though, is 92 million miles away from us. And as we also said, interestingly, the disk of the moon this close to us just happens to be the same relative size as the disk of the sun that we're seeing far, far away. And recall, there was no reason for that. God just did it for some reason. Anyway, here we are at 10 o'clock Tuesday morning. Eclipse day, right? And look at this. We didn't see this planet right here. Actually, you did. You would see this if it was clear where you were looking and the eclipse totally covered the sun. But right at the moment, there's a little bit of sun still peeking through right here, because look at this line. The moon is on this thing called the ecliptic. The sun is on the thing called the ecliptic. Jupiter and Uranus are on the ecliptic. Venus is on the ecliptic. What else? Mars and Saturn. So I think we can make a rule here that says the planets and the moon and the sun appear to be all on the same line. And I don't know if you realize that or not, but if you go out any night and look around, if you see a planet here and a planet here and a planet here, you're not on planet Earth, you're somewhere else. Because as long as you're on Earth, every single planet will be pretty much on the same line, and not exactly. You see, some of these are off 2 or 3 degrees. That's off a few degrees here. But the planets will be back and forth on this thing called the ecliptic, and so will the moon, and so will the sun. In fact, the ecliptic is defined as the line of the sun going, or the sun and the earth going around the sun. So the reason we see the sun on the ecliptic is because we're looking at the ecliptic when we see the sun, regardless of where the sun is. Now, think back again. We're about 3 hours away from the eclipse right here, and the moon that we're seeing hasn't quite covered the sun right here. And actually in Rogers it won't. You'll still see a little bit of it sticking up, because do you notice right here the moon isn't exactly on the ecliptic? I have the fortune right now of knowing that tomorrow my moon will be up a little bit, and it will literally cover the sun completely. So the path of totality only happens for those who have the moon exactly centered on the ecliptic, because the sun is exactly centered on the ecliptic. Now, here's a good time to ask this question. Why don't we see an eclipse every single time the moon goes around? In fact, let me show you tomorrow's moon. I think if I go plus, look at that. Tomorrow at exactly this same time at 10 o'clock. Actually, I'm sorry. Today, right? The day that you're watching this, Tuesday. Look at that. The moon right now in your class probably is right there. Now, it's hard to see because it's black. We're looking at the back side of it. And you'll notice it's up above the ecliptic. So we don't have an eclipse that day because the moon has moved this far away. I'm going to move it one more day down. Oh, and look at this. We're starting to see a little bit of the lit side of the moon right here. So 2 days, tomorrow actually, which for you will be Wednesday. If you go out at about 10 o'clock, you can't see it because it's daylight. But tomorrow night or Wednesday night, you'll start to see a little sliver of a moon right here. Because here is the moon, we're looking mostly at the dark side of it, and we're this far away. We're about 25 degrees away from where the eclipse had happened several days ago, or 2 days ago. And in fact, let me do this exactly. So, very interesting. And if we keep this thing going, let me turn on daily motion and just watch what happens. Or let's do it this way. I'm going to go back to my eclipse. So here's what I'll be seeing. And in fact, let me do this exactly. I'm going to set it precisely to my eclipse that I will be seeing right here. So I'm going to speed it up just enough. 2 o'clock. That's when we want it. Move that moon a little bit. And then I'll show you what it looks like. Close enough. 13, 1, something right there. I can go a little faster. I'll try to stop this around 2 o'clock. That's when we want it. And hopefully that's what. Let me do the time first, and then I'll show you what it looks like. Look at that. Close enough. 13, 1, something right there. Okay, so let's look at where the ecliptic is right now. And hopefully that's what I'll be seeing tomorrow at exactly 1:39. Look at that. A perfect moon sitting right on the ecliptic with the sun right on the ecliptic. And we barely see the corona of the sun behind it. And that's why eclipses are so useful, because we can literally see for the first time the atmosphere of the sun without having to see the bright part of the sun that's directly in front of it.